What's up, everybody? Welcome back to Kev the Dev. Today we're going to be talking about concurrency in Python. I wanted to go over quickly some of the differences between using single-threaded approaches, multi-threaded and multi-process approaches to solving problems using Python. So I don't really want to talk too much. I just kind of want to dive right in. So I'm just going to go for it. So if you want to follow along, make sure you got your terminal set up with a recent version of Python. I think I'm using 3.8, and then have an editor up that you can edit these files in. So let's get going. So the main thing that I wanted to go over here was how you can leverage concurrency using Python to solve problems. So it's hard to sort of discuss theoretically. So let's just make a problem and do it single-threaded, and then we'll iterate over that and adjust to using multi-threaded. So first, I've got this folder, an example folder. I'm going to touch a few files. So we're going to do single thread. We'll make a file for multi-thread, and we'll make a file for multi-process. And we'll talk about what the differences are between those shortly. Okay, so then I've got my PyCharm editor over here. All right, so we're going to start in single thread. And what I want to do is make up a problem that we will solve the traditional way, and then we'll observe the performance and we'll compare that performance against these other approaches. So the first thing we're going to want to do is come up with some sort of thing that does a workload. And so one of the things I like to use for examples is just summing numbers together. So let's do our standard, if our name is equal to, if our name is equal to main, so then we'll invoke some sort of function. Okay, so let's write that here. So we have this main function, and we want to essentially just do something. Like I said, summing a bunch of data together. So let's get sum. We'll use the built-in sum function to get the sum of all numbers between 0 and let's see, 1,000, million. Let's do 100 million, and I think that'll be enough numbers that it will take a good bit of time. And we can actually capture that time using one of Python's one of Python's libraries, the time module. So we'll import time. We'll set a tick equal to time.perf counter, and that's going to get the exact moment that we invoke that. Then we will try and get the sum. Then we'll get the time again, and then we're going to go ahead and print out that the execution took, and then we'll do talk minus tick. We're going to take that to 4 decimal places, and we'll say it took that many seconds. Okay, so as soon as we invoke this function, it should get the sum and tell us how long it took. So let's try that. So in your terminal, let's make sure I've got it here. Yep. All right, so I'm going to run Python single thread, and we'll see how long it takes. Shouldn't be more than a couple of seconds. Okay, so 2.74 seconds. Now this will vary depending on what type of processor that you have on your machine. Okay, so that is our baseline, right? That nothing here stands out to you probably. This is very familiar with a traditional imperative programming approach. But what if we needed to do something like this, something like summing multiple times, right? So single thread, we do it again. Maybe it's a different set of numbers, but I'm just going to keep it the same for simplicity. But the point is, you could have an arbitrary number of these units of work that have either maybe they're discrete sets of data or they're somewhat overlapping. Whatever the case may be, you have these sets of things that you want to operate on, right? So if we add this to the single thread, what do we think it's going to be in terms of execution time? Let's run it. Yep, so it took 5.46 seconds. So that's roughly double what the single-threaded, what the single sum approach was. And that makes sense, right? It has to do all the work in one thread, then it does it all again. So of course it's going to be roughly double of what the original execution time was. But don't you think there should be a way to do those two things in parallel such that the execution time is not going to be double? And yes, there is. So first we're going to take a look at the multi-process approach, right? So let's open up a new file, multiprocess, and we're going to do a couple of things differently. We're going to do the same if name is equal to main, then we're going to execute some function, which we will define here. Okay, so that single thread is also single process. A thread has to run in a process. So what we want to do is try and demonstrate how we can solve that problem using multiple processes. So let's copy over the work, the function here, into our main function here. All right, so this looks the exact same, right? And we could test it, we could run it, and it should give us the same result. We'll want to import time again if we want to time things. But what we want to do is we actually want to take the work unit, which in this case is getting the sum of something, and we want to actually execute that multiple times in separate processes, right? And so the way you do that in Python is we're going to, from the multiprocessing library, we're going to import the process class. Okay. So this object is going to let us set a target function that will get executed when we spawn that process. All right, so let's do that. We're going to, let's rename this function get sum. So this is going to be the unit of work, okay? Let's start fresh. All right, so what we want to do is we want in this function, we definitely are going to still want to get the sum. So we'll just keep this simple. It'll be a sum of range of 0 to, let's see, 1,000, 1,000,000, 100,000,000. Okay, so this is going to get that sum. But if we just execute this, well, let's get sum. Then that's going to just, and we run this function here, that's just simply going to get the sum one time. But what we're going to do is we're actually going to spawn multiple processes. So in our, we could do this actually. Let's keep it consistent with how we did it before. So I'll make a main function here. And then within this function, we are going to create a process. So we'll call it P1 and we'll make a process. Now processes take targets, right? Same as threads. So we're going to set the target to be that get sum function. Okay, so now all we've done here is create a process. We haven't run it yet, right? So you know what we'll do? We'll get we're going to get the starting time in a moment, but let's create another process first. So we'll make another process with the same target. Okay, so again, this is a very simple way of creating these processes, and you can get a little fancier, but we're just trying to keep it simple here. So we've made two processes, but we've done nothing with them yet, right? So in order for us to actually get these processes flowing, we have to call start on them, right? So that's going to start that process, which is going to kick off the sum function. So you know what we'll do, just to illustrate this, we're going to comment out that P2, we're just going to run P1, okay? And then we will time it. So let's do our tick equal to time.perf counter, and then we'll do talk equal time.perf counter, and then we'll print out execution took talk minus tick to 4 decimal places. Seconds, okay? All right, so we're going to start the process. We're going to capture a time after we ran the process, and we're going to run it out. Let's see what happens. You'd think this will be printing out that it takes roughly 2.74 seconds. It won't be exactly the same, but it'll be roughly similar, right? That's what you would think. So let's try running the multi-process code. And what do we see? It's not what we expected to see. It looks like it took no time at all. But if you noticed, we'll run it again. It actually isn't done yet. See how it's still blinking and then it finishes? Actually, it's finishing in about 2.74 seconds. But the time that it's telling us is it's this low because of the way that processes are managed in Python. actually in your operating system, but we'll keep it abstract for now. And what I mean by that is, let's step through each line here. And this is going to be important for threads too, because this behavior is very similar. So we create our process here, but so far we haven't done anything with it. It's just an object in memory, right? It has a target, which is a function, which is this getSum. Next thing, we capture the time, okay? This seems pretty standard. Next thing though, we start the process. So what that does is it forks a new process in the operating system, and it runs that function. But the thing is, that new process, that is its own life cycle. So as soon as that new process starts, we now have two processes, right? We have the main process, which is running this main method, and then we have this child process, which is running getSum. So as soon as we start this function, the main process continues going. It's not waiting for that process to finish because it's doing its own thing concurrently, which is the point, right? So as soon as it finishes starting, it captures the exit time, and then it prints it out immediately, even though that other process isn't done yet. Okay, so how do we solve that, right? Well, that's what the join method is for. So we can call join, which essentially says to Python, I want you to wait until that process is done, and then we'll continue on, right? So this is executed ideally in the main process. Here it is. And again, we're keeping it simple because this can get very complicated. So now if we run it, we should get exactly what we saw with the single threaded. It took about 2.7 seconds. And that adds up, doesn't it? It's one process that we're running, we're starting it, we're waiting for it, and then we're timing it. Makes sense. So how do we optimize that, right? So let's say in the single thread example, let's see, where was that? Right, we just did the sum 2 times in a row. So what we're going to do here is we're going to create two processes, P1 and P2. So we're going to do P1 start, and right after that, we're going to do P2 start, okay? And then we'll do P2 join. So now what we're doing within our timing, within our timer, we're going to start both processes, and then we're going to wait for both processes to finish. Then we're going to finish our timer. We're going to stop the stopwatch, right? And then we'll output. So let's see what that does. Multiprocess. Now look at that. It took 2.87 seconds. So that was much faster than the single threaded approach, which took 5.46 seconds for doing the same amount of work. And again, this can be dug into much deeper, and I encourage you to check out the documentation on concurrency and parallelism in various textbooks or links. I'll post a few below for the Python related ones, and I definitely encourage you to look into those because they're very interesting and they can get very complicated, but they're useful. As you can see here, all we did was add a little bit of extra code, and we were able to take advantage of my computer's multi-core processor, which has 6 cores. And when you're only running one thread, those 6 cores aren't being utilized as well as they could be, right? So every time we make a new process, we ask the hardware, do you have a core that this can run on? And when there's a free core, it runs on it at the same time as things running on the other cores, right? So that's parallelism, when you have 2 things running at the exact same time. Now, if you have a single core available, whether you're in a VM or you have only one core available for user land, whatever the case may be, then you're going to run into concurrency. You're going to have very different results here because you're going to have one hardware core running 2 processes. Now, that's not parallel, but that is concurrent, right? You have these 2 things overlapping. And again, please read the documentation posted below on concurrency versus parallelism because they are there is an important distinction between them. Okay, so now that we've gotten the process discussion out of the way and we can see with our eyes the results that using multi-process approach can be, let's talk about threads. Now, threads are very similar, and in fact, they're so similar, I'm just going to copy this whole script and paste it into my multi-thread. And all I'm going to do is I'm going to get rid of that import, and I'm going to import, actually I'll say from threading. We're going to import thread. Okay, so we've got thread now. So all we're going to do is replace process with thread. That's it. The API for thread and process, those APIs are very similar. And please read those as well. They both have a target, and they both have start and join. And at the surface, they're extremely similar. In Python and in Ruby as well, but obviously we're doing Python here. In Python and Ruby, the distinction between them is very important, okay? So we're going to try and do, just without talking anymore, we're going to go and dive in and we're going to talk about what we see. We're going to run this using threads instead of processes. And we're going to see, well, let's just see what happens. Let's run it now. Multithread. Python multithread. Oops. Yeah, okay. So we start the threads, we join the threads, we time it, and it takes 5 seconds. Now, that's not what we want, is it? We should be seeing 2.7 seconds or 2.8 seconds, just like we found with the multiprocess. What's going on here? Again, I encourage you to dive into this more, but quickly, the issue at hand here is that in Python and in Ruby, there is this thing called the global interpreter lock. And what that means is within one process, every thread has to have the global interpreter lock in order to execute Python code, okay? So here we're creating, let's rename these so they're easier to read. We'll call this T1 instead of P. All right, so these T1 and T2 threads, these threads, when they are spawned or when they're started, they receive the Python global interpreter lock because it knows that thread was spawned from a parent process. Okay, it's not an independent process like these were. These get their own memory space. They're a lot more overhead than threads. Okay, so in threads, they share a lot of memory with other threads that were created by the same process. Now, T1 and T2 have the same target. We start the timer and we start T1. Now, what happens is that global interpreter lock is now held by T1. T1 gets started and it doesn't release the lock, which means that the main thread, the thread running this file that we're looking at, is waiting. It can't even start T2 because T1 is running a CPU-bound operation that does not release that global interpreter lock. So this sum function is going to hold on to that lock and prevent other threads from executing. So as soon as it finishes, that's when the main thread can resume, right? So we finished this line 11, now we're down at line 12, and it starts that process all over again. Okay, so we start the threads and we wait for the threads and then we time it, right? And we notice that it's basically no better than doing it sequentially because under the hood, it's really doing it sequentially. And that's again because of the global interpreter lock, which is unique to the Python and Ruby interpreters. If you were to run this in Java, the Java JVM does not implement it that way. And that's that was a design choice by the creators of Python and the creators of Ruby to do it that way. Again, documentation. I'll post the link below as to why that choice was made. And it wasn't necessarily a bad one, but it was intentional. Okay, so maybe you're thinking to yourself, why would I bother using a thread? It doesn't do anything for me. Well, it's not entirely true. The distinction here is, remember how I said it's CPU bound? So it's not releasing that lock because it's executing Python code. Well, there are many types of work that are not CPU bound, okay? Maybe here you're read, write from file. Or maybe your execute HTTP call. Whatever that unit of work is, you are not CPU bound, you're IO bound, right? You're waiting on IO from a pipe, from some WebSocket, or from local input, or read write from a device, whatever that is. That's not CPU bound, okay? And now the reason that matters is that underneath the hood in the Python source code for threads, there is functionality that specifically releases that global interpreter lock during IO operations, okay? Because Python knows, hey, I'm waiting on something. I don't need to hold this lock anymore, okay? Now, there are more complicated ways to demonstrate this, but I'm going to show you an easy way to demonstrate the distinction, okay? So one such operation that uses IO is the sleep operation, because when you execute the sleep operation under the hood, it's actually invoking a system call, which then it waits for the results of that system call. So while it's waiting, it does IO. it asks the system for information, and while it's doing that, it's releasing that lock, and it allows another thread to execute while it's waiting, okay? So we're gonna sleep for 1 second. That's it, that's all that function is gonna do. And now when we run this, what do you think is gonna happen, right? It's gonna sleep for 1 second. You might think, well, if it was sequential, sleep for 1 second, then sleep for 1 second, this is gonna take 2 seconds. Let's try, multi-thread. How long does it take? 1.01 seconds, okay? Now, again, the reason for that is the thread released that lock while it was sleeping. It was an IO bound operation, and the thread was able to execute, both threads were able to sleep for 1 second at the same time. Now, that's different than what we were just seeing before with CPU bound operations like summing a bunch of numbers together. All right, that's it for today. If you have any questions about more detailed questions, I should say, about concurrency, parallelism, please post them below. I would be happy to answer. I'm going to try and do this with some other languages to show the differences between how concurrency works across different runtimes. So thanks, everybody, and have a great day. And if you enjoyed this, please like, comment, and subscribe. See ya.